Okay, in this video we're going to look at some examples to do with linear combinations of vectors. And this is a pretty mathematical thing that we're going to do here, but it has a lot of applications. So we're going to go ahead and do this, and then I'll maybe talk about some of the applications that you might see this in other classes or other places in your studies. All right, so we want to write a vector here, J, it's one of those standard basis vectors, as a linear combination of two other vectors here. And these are all given in this IJK notation. So if you're more comfortable using the component forms of the vectors, one of the things that you might do at the beginning of the problem is just rewrite all of these in their component forms. So J is 0, 1, 0, and then these two vectors here could be rewritten as 2, 0, negative 3. So 2 in the I component, 0, J, negative 3 in the K component, and then the W vector could be rewritten as negative 2, 2, 1. So again, you want to develop some fluency going back and forth between those two different notations. Our textbook uses both. I will use both in assignments and anything I do with this class. So, all right, so what I want to do here is think about writing this vector as a linear combination of these other two vectors, or show this is impossible. All right, so let's think about what that means. So we talked about linear combinations a few videos ago. A linear combination is when you take a sum of scalar multiples of two objects. So the idea here is that I want to show somehow, if possible, that J, I'm going to use the component form here, 0, 1, 0, is a sum of scalar multiples of these other two vectors. So I don't know what those scalars might be. Sometimes students just start by trying numbers, but that's not usually a very efficient way to do that. But I'm just going to use A to represent some unknown scalar here, times one of the vectors, plus B, another unknown scalar, times the other vector here. So what I want to do is find scalars A and B that make this equation true, or show that that equation is not ever true. All right, so in order for vectors to be equal, their components, corresponding components, would have to be equal. So one way we can do this problem is by separating this into really three equations, a system of equations, based on each component. So in the I component, or in the first component of these vectors, for this one I have 0, and that would have to equal what I'm going to get in the first component if I go ahead and simplify and combine these two, 2A minus 2B. Right, so what I've done here, this is all just the first component of the vector on the left side, and then the simplified first component from the right side here, 2A minus 2B. And then in the second component, I have 1, and then over here I would have 0A, so I'm not going to write that, and then plus 2B. And then in the third component, I would have 0 equals negative 3A plus B. All right, so what I have here is a system of three equations in two unknowns, so an overdetermined system. So when you have a system like this, you want to try to, you might know many ways to solve a system. Whatever way you know to solve a system is perfectly fine. This one's pretty straightforward. This second equation, the B solution, falls right out of that second equation. So in this second equation, I get B equals 1/2. And then if I plug in that B equals 1/2 into, say, the first equation, I get 0 equals 2A minus 2 times 1/2 will be minus 1. And then I solve that for A. I'll also get A equals 1/2. All right, so I got those A and B values by using my first two equations. In order for this to satisfy that system, though, it also would need to satisfy this third equation. So I would need to check in that third equation to see if these two work. So if you check, you should notice that those don't work in that third equation. 0 is not equal to negative 3 times 1/2 plus 1/2. Right? This does not simplify to be 0. So it does not check in that third equation. So what that means is that there are no scalars, A and B, for which this is true. So this is not possible. All right, why I might be interested in whether that's possible or not is if, for example, these vectors represented forces, and I had 3 different forces acting on an object, but one of the forces was perhaps a sum of scalar multiples of the other 2 forces, then perhaps that would mean some things about being able to simplify the problem. It also has to do with things like data compression, that when you do things like data compression, this is essentially what you're doing, is writing one thing as a linear combination of some other kinds of objects that you have stored for the data compression. So it has a lot of practical applications. I'm just going to kind of modify this example just a little bit just to show you a similar problem, but where it does actually work here. So we are going to change this a little bit, and we're going to write a different vector as a linear combination of this v and w vector. And this one actually does work here. So we're going to try a vector 2, 3, -6. And I want to try to write that as a linear combination of these 2 vectors that I've started with. So I'm just going to start with the same strategy here. A times one of my vectors plus b times my other vector. Write my system of equations. So in the first component I have 2, and then over here on this side I'll have 2a minus 2b. And then in the second component I'll have 3 equals nothing for the a and 2b. And then in the third component I'll have -6 equals -3a plus b. Okay, again, solve a system of equations. An overdetermined system again, 3 equations, 2 unknowns, so you solve the system however you know how to solve that. This one's pretty easy again. The b falls right out from one of the equations, and then you can substitute that in. In this second equation, if I solve for b, I get b equals 3/2. And then if I substitute that into another equation, say this first equation, I get 2 equals 2a minus 2 times 3/2 will be -3. If I add the 3 and divide by 2, I get a equals 5/2. Now I told you that this one's going to work, but if you didn't already know that, you should check that this a and b does work in this second equation, or in this third equation, the one I have not used yet, whatever equation you haven't used yet in your algebra here. So I'm going to check to see if those 2 things really are equal. -6 is equal to -3 times 5/2 plus 3/2. And sure enough, I get -15/2 plus 3/2, which is -12/2, which is -6. So yes, that does check. So that works in that case. This vector can be written as a linear combination of those other 2 vectors. Really, if I want to write my answer the way the question was stated, write a vector as a linear combination of the other 2 vectors. This is all of my work, but I probably should go ahead and put my a and b vectors in here. So I'll have 2, 3, -6. And then I could write my a vector, or my a scalar, 5/2 times. I could write out my vector v, or since I have some notation for that, maybe I'll just write v, 5/2 times v, plus 3/2 times my vector w. So there, I now have my vector written as a linear combination of the other 2 vectors that I was given. So again, it's very mathematical, just doing a lot of algebra really, but a lot of practical applications. And so you'll see this some other times in this class, but you'll certainly also see it in physics class and in linear algebra as well.